Okay, welcome back. We continue, and the next step is actually to make the ground, the terrain, right? So yeah, the terrain. Let's have here a vector of floating of floats. Let's call it Heightmap, because Heightmap it is. And let's initialize these guys. Let's go ahead and say, let's initialize, I don't know, 100 guys. No, not like that. Let's say 100 guys. Physics pushback 0. We will start with flat terrain for now, just for testing. Yeah, and we need to draw also the height map. I equals 0. I is less than physics. What? Physics height map size I plus plus, and yeah, no, I don't like that. So yeah, we need to calculate how many height map points we need to render, right? And let's say here, let's define world, actually heights per meter. Or per pixel. Let's go per meter. Let's start with 1. And now here we need to go and times camera width. Because the width is, no, it is not. Right. Oh, this is going to be bad. Definitely. Index is going to be I. We need the left index. Well, let's make things simple for now. Let's just go ahead and draw the first 100, or let's draw everything. Physics Heightmap size, and we need actually to go -1 here. if we have that, because this is unsigned. Draw shapes, draw line. What is it? It is a vec2 of the I, and physics Heightmap of I for the Y, and that is +1 for this one, +1 for this guy. Thickness, I don't know, let's go like this. And the color, let's go for green for the grass. Okay, let's run it. Okay, yeah, this is the beginning of the terrain. Yeah, and this is the line. Let's initialize this thing, the simple particle, with mass and the same radius, and the position is going to be vec3. No, vec3 0. Let's go 4 meters up, and do we need anything else here? I think no. That would be okay. Yeah. And now we need to calculate the static collisions with the ground. Okay. Now, in order to do that, we must find the particle position on the x-axis. So the index is going to be the particle position on the x-axis, and that is a float number, and we will float and then cast it to a UI32. By the way, UI32 stands for unsigned integer 32-bit wide. So cast. Normally it is like this. It is a uint32. See, but I don't know. UI32 is faster for me, at least. Like this. And we also need to compute the gradient, right? So let's call that left and right is going to be left +1. And the gradient is left position. Yeah, Heightmap of left. That's for the right position. So now we have the actual positions in the world, the world positions of the two heightmaps, sorry. And the gradient is going to be the difference of these guys. Minus the left position. So now what we did is, let's say we have not you. We have, if you remember, we have separated the terrain in discrete values, heightmaps like this. So what we do here, this left guy is that guy, let's say, and the right guy, it is the next one always, so it's this guy. And we calculate these two positions, we calculate that position, and when we subtract the two positions together, we're getting that vector, like this. So now we have that vector, and we need to have the perpendicular vector which is pointing to the normal vector. Yeah, we need that vector, which is 90 degrees of this vector. Okay, so how we do that? Let's what we can do is simply we can just rotate that, or we can multiply by 90 degrees. But just in case someone wants to extend this thing in a 3D world, we will do it in a proper way. So all I need to do is I need to have normal is the cross product between the unit Z and the gradient. Okay, and we need to normalize. Actually, we need to normalize this guy as well. Let's call that offset. And normalize that. And normalize also that. Okay. And now we do have the normal here. And we do need the normal in order to reflect the velocity of the ball. If the ball going and hit the ground, then the velocity of the ball must be reflected based on the normal force. Is it the right word? I'm not sure. Based on that normal, we're going to flip the velocity. We also need the contact points. Normally in the physics engines, first you calculate the contact points on each pair. I'm not sure we will need that here. All we need is to calculate the contact point for each particle, right, to the ground. And the contact point, it is, if it is a contact point, it's going to be always the part. Let's specify here const the contact point. The particle position, the y, minus the particle position, no position, radius, right? And all that is going to be no, this is wrong. It is the particle position minus vec3 of 0 and 0. So wherever the particle is minus the radius of the particle, it is the potential contact point with the ground. Okay, now we need to specify the plane, the normal plane, and the normal plane is going to be a vec4 and I'm not really sure where I have found this equation. I tried to remember how I derived that, but I really don't remember. And it is vec4. If any of you guys know how that thing works, please let me know in the comments, because I really don't remember. But it is the normal of our surface for the x, y, and z, and for the w component, it is the dot product between the normal and the position of the line. The position of the line is let's call that plane position. Plane normal is lerping function in left position. I know it is just the offset, but right position, just the half of the offset. We just calculate that above. All I have is divide by 2, but just in case we need to make any changes to the offset, so we will not break the rest of the code. That's why I like to do separate a complete line of code as much as possible. 0.5 like this. So that's the plane's position here, and plane normal and plane normal. Nice. So this is our contact plane, and this is the potential contact point. We need to test these two guys. We can check it by compare it by the dot product between these guys. Contact Yeah, let's make that like 4. Like 4 is 1 here. That is simple to we setting 1 here just for the dot product to get the raw dot product of these two guys between the contact point and the contact plane, and if that is less than 0, then we have a collision with the ground. Actually, hopefully we do. Let's store that value. F32 contact. That is the penetration value actually. How deep we are inside the ground. I believe it's called F. I don't know. Let's say contact depth, and that is equal to that. And if that depth is less than 0, then all we have to do for now, for the static collisions, is to move the particle up by that contact depth. So particle position plus by the normal, right? By normal times the contact depth. Yeah. Yes, I believe that is. And the velocity is going to be equal, or shall we add? No, let's make it equal. And we are going to reflect by the indice is the velocity itself. And the normal is the contact. It is the plain normal. And you know, when you have so much codes inserted into your project without testing, it's like 100% sure that something will go wrong. Okay? Because I'm not copy pasting here, I'm writing everything now. I have made similar projects, but I'm not using copy paste, or I am not looking anywhere. I just writing right now. Okay, let's build. Let's see why this will not work, or something else crazy will happen. Will happen. Let's see. Oh yeah, nothing at all. Maybe do we update collisions? No, we don't. Okay. Let's update that. Let's build them. Whoa, that was not Let's see. This is minus 7.67. Come on. Particles. And after that, it is upwards. That is correct, isn't it? Oh, okay. I see, and then probably reverse it again, right? Hide item to watch, please. Particles. Yeah, and then goes minus. We go back. So this guy doesn't work properly. Why? Okay. What? That's our position, and yeah, that goes down, but we do need to move it up. We're adding the plane normal times the quarter depth. Do we have to subtract this for some reason? I'm not sure. No. Oh, the plane normal must be incorrect. Yeah. Okay. Why that needs to be reversed? Makes no sense. The normal is wrong, definitely. It is pointing up. This is pointing to the right. The plane normal, it is correct. What's going on? Oh yeah, we are minus here, right? We need to offset like this. Okay, there we go. Because we are already inside, so we must inverse that guy. Okay, so yeah, we have this thing. Now this looks like okay, it is bouncing. It is going up and down anyway. And let's say add a few more, shall we? Let's move everyone actually more to the right. Let's go 10 meters to the right. And oh, what? No, not you. Okay. Let's add one more guy to 12 and one more to the 14. Yeah, let's make this guy to be 5 meters in height, and if we run that, yeah, okay, that looks promising, but we are not sure if this thing is working yet, so let's check that. Let's add some gradient here. So let's go with a randomizer. Yeah, let's do it like this. It will be no. This will be too much extreme. Times 1. Let's see. Why the line is this still straight? Come on, you can do it. Oh, okay. It is too small, the values, I think. Yeah, there we go. Oh, that's bad. Okay. Is that a minus here? No, it cannot be, right? It can't be. Well, yeah, that is. Yeah. Now the problem with the assertion there is because we reaching here and we are going minus. Let's get here the maximum value of 0. And that guy, so that will not happen again. Yeah. Okay, that looks promising. Of course, now these are elastic collisions. I mean, they will bounce forever because there's no friction yet. But yeah, that looks very nice. yeah. And I will see you all in the next video, where we will continue with springs.